Right now, if Voyager 1 fell silent at this exact moment, NASA wouldn't find out until tomorrow. Deep inside the Jet Propulsion Laboratory in Pasadena, a quiet monitor tracks this very delay. It measures the distance between us and our farthest creation. Right now, that number stands just under 24 hours. Let that land for a second. Send Voyager 1 a radio pulse right now. It will leave Earth at 300,000 kilometers per second, the fastest speed this universe permits. Yet before that pulse can even bridge the gap, this planet will complete a full rotation. Sunrise, sunset, the entire arc of a human day will pass, while our voice is still crossing the dark. That is where Voyager 1 is today. Around November 13th, 2026, it will cross a line no human object has ever crossed. One light day from Earth, 25.9 billion kilometers from home, 16.1 billion miles. At that moment, something fundamental changes. Not just the number. The nature of our relationship with this machine changes in a way that no engineering fix can solve, no budget increase can address, and no future technology can reverse. Here's what I mean. When engineers at JPL receive a signal from Voyager 1, they are not looking at the spacecraft as it exists today. They are looking at a ghost from 24 hours ago. The present moment between us and this machine has been permanently erased. Think of it like trying to love someone from a distance so vast that every message they send arrives a day late. By the time you read their words, their reality has already changed. You can write back, but your reply will spend another day crossing the dark. A continuous 2-day delay where neither side ever captures the other's now. That is what the teams at the Deep Space Network deal with every single day. They write commands into the future. They read confirmations from the past. One light day is the moment that delay stops being an inconvenience and starts being the permanent condition of the mission. And it is not getting shorter. Every day, it gets 11 seconds longer. Now, from where Voyager sits right now, what does the universe actually look like? In 1990, Voyager was 6 billion kilometers from the Sun. Close, by today's reckoning. Carl Sagan used the last gasp of battery power in the spacecraft's cameras to turn it around and take one final photograph of Earth. What came back was the pale blue dot, our entire world. Every person who ever lived, every war, every love story, compressed into a single pixel of pale blue light, hanging in a beam of scattered sunlight. That photograph was taken from 6 billion kilometers. Voyager 1 is now more than 4 times that distance from home. At one light day, Earth is not a pale blue dot. Earth is not visible at all. The The cameras have been off since 1990, shut down to preserve power, a decision we will come back to. But here is the hard truth. Even if the cameras were running, our planet would not register. It would be drowned in the background noise of the galaxy, indistinguishable, gone. The sun is still there, but it is not the sun you know. From where Voyager sits right now, that star, the one that burned your arms on a summer afternoon, is just another star, not the brightest in the sky, not dominant. It sits there, cold and point-sharp, roughly as bright as Venus looks to us from Earth on a clear December night. There's no heat behind it anymore, no pull of home. It is a reference point, a navigational landmark telling the spacecraft which direction it came from. Jupiter and Saturn, the gas giants Voyager visited in 1979 and 1980, worlds that could each swallow 1,000 Earths whole, are not visible. Too faint? Too far? Lost in the general background illumination of a star they orbit from incomprehensible distance. The entire solar system has been compressed by distance into a single pale point of light. This is what leaving home actually looks like. Now here is the part of this story that I think most people have never been told. And it is the part that makes every data transmission coming back from Voyager one feel less like engineering and more like a miracle. We have always imagined the space between stars as empty, a perfect void, a nothing so absolute that the word silence does not quite cover it. Textbooks say it, documentaries say it. The popular image of interstellar space is a vast, featureless black. Voyager 1 crossed into that space in August 2012. It punched through the heliopause, the outer boundary of the sun's magnetic bubble, the shield our star has been projecting outward for 4.5 billion years. The spacecraft became the first human artifact in the history of this species to enter interstellar space. And the instruments did not go quiet, they lit up. What Voyager found was not emptiness. The plasma density outside the heliopause is measurably higher than inside. The interstellar medium is not a vacuum. It is a thin but real pressurized medium of ionized particles. The dispersed remnants of stars that died before our sun was born. Stellar ash and stripped electrons drifting through the galaxy for billions of years. Forget the calm winter morning analogy. This is not a gentle pressure against your face. Voyager 1 is moving through radiation. It is pushing through plasma compressed by the bulk magnetic field of the Milky Way. Beyond the heliopause, the spacecraft is no longer protected by the sun's magnetic umbrella. It faces galactic cosmic rays, high-energy particles accelerated by distant supernovae, some of them moving at fractions of the speed of light. These particles hit the spacecraft constantly, steadily, without pause. The hull of Voyager 1 absorbs that bombardment every second of every hour of every year. In December 2018, the instruments detected something scientists had not predicted. A constant hum, a steady, low-frequency vibration in the plasma of interstellar space. a background noise the galaxy itself generates, the electromagnetic signature of the medium between the stars. Not a burst, not a pulse, a hum, permanent and pervasive, like the sound a transformer makes in a wall, except the wall is the Milky Way. Then in 2020, even in clear interstellar space, the magnetometers registered an unexpected spike in the field density around the spacecraft. The Sun, billions of kilometers behind the spacecraft, had sent a pressure wave outward. Solar activity so powerful it temporarily pushed the heliopore's boundary itself, all the way out to where Voyager was sailing. A slow-motion shock wave crossing the entire system. The boundary we had mapped breathes, contracts and expands. The edge of our solar system is not a fixed wall. It is alive. None of this appeared in any prediction before Voyager crossed it. We did not know. We could not have known. The only way to find out was to go there, and we sent a machine the size of a school bus to do it. Which brings us to the machine itself. Because to understand what a one-light-day milestone actually means, you have to understand what is keeping this spacecraft alive, and for how much longer. Voyager 1 is powered by an RTG, radioisotope thermoelectric generator. Inside its body, rods of plutonium-238 are decaying, slowly, predictably. Converting radioactive heat into electricity through a process that has no moving parts, makes no noise, and produces no exhaust. It is one of the cleanest, most reliable power systems ever built for space. At launch, the RTG produced roughly 470 watts. Today it produces less than 230. Every year, it loses approximately 4 watts of output. 4 watts. On your electric bill, 4 watts is invisible. In your house, 4 watts is the standby power of a television remote receiver. Meaningless. On Voyager 1, 4 watts is a life-or-death decision point. The engineers at JPL have been rationing power for decades now. Every system they switch off buys a few more watts for the science instruments. The magnetometer, the plasma wave spectrometer, the cosmic ray detector. The instruments actually doing the work of exploring interstellar space. The cameras were shut down in 1990. That bought time. Redundant heaters were disconnected. That bought more time. But it came at a price. Parts of the spacecraft now operate at negative 79 degrees Celsius. Colder than the coldest winter ever recorded on Earth. Cold enough to crack most materials. No engineer in 1977 would have signed off on those conditions. The electronics have held. The transmitter puts out 23 watts of radio power. 23 watts from 16 billion miles away. By the time that signal reaches the dish at Goldstone, the power arriving is less than 100 quadrillionths of a watt. To put that in human terms, a single 60-watt light bulb produces more power than 20 million billion Voyager signals arriving at Earth simultaneously. To catch a whisper that faint, the deep space network must combine giant antennas across 3 continents, straining to pull Voyager's voice out of the background noise of the universe. They have done this every day for 48 years. But sometime in the late 2030s, the nuclear heart will finally drop below the minimum threshold. The signal will vanish. After that, Voyager 1 will not stop. There is no atmosphere to drag it down, nothing in the void to fall toward. It will simply continue at 61,000 kilometers per hour, blind, silent, and frozen, drifting for 40,000 years toward a faint star called Gliese 445. But there is something aboard Voyager, one that will not go silent when the RTG does. It is called the Golden Record. We've broken down the deep, complex history of this gold-plated copper disc in a previous video, but its core mission remains simple. It is a time capsule carrying our greetings, our music, and our existence into the deep. Carl Sagan is gone. The engineers who built it have passed away, but the record travels on. On its cover, a drawing of a man and a woman still sits in the dark, waving, and that is what strikes me most after sitting with this story for a long time. The people who built Voyager 1 in 1977 knew they would never live to see its destination. They accepted a mission to design a machine for scientists who are not yet born, to answer questions that had not yet been phrased. That sacrifice has spanned half a century. These were engineers who chose to cut off the internal heaters, forcing the spacecraft to operate at negative 79 degrees Celsius just to save the final 4 watts of power for the cosmic ray detector. These were researchers who dedicated their entire lives to analyzing a single strip of plasma hum, knowing their life's work was merely a thin page that only their grandchildren's generation would finish. That mindset is no different from the builders who laid the first stones of ancient cathedrals. They carved rocks to build foundations, knowing they would rest deep beneath the earth long before the spire ever pierced the clouds. They did not do it to meet a commercial deadline. They did it because they understood a fundamental truth. Some great things can only be created. When humans accept to dedicate themselves to an ending they will never live to see. Voyager 1 is that, a cathedral aimed at the stars. On November 13th, 2026, it will still be in recent memory, passing the 1 light day threshold. The RTG will go quiet, the signal will fade. The day will come when no dish on Earth can hear it anymore. But the record will still be there, still waving. We built something that is now 1 light day from home, crossing interstellar space, carrying our music into the dark. Space is hard, the distances are unforgiving, but we went anyway. That is the most human thing we have ever done.